Basic analysis techniques for simple random samples assume that the sample is drawn from a large population, or that the sample is selected with replacement. What if the population is small? Let us say we are studying the populations of two villages. One village has 80 households, and the other has 240 households. In terms of sampling, both of these populations are small, but the fact that one is smaller than the other matters. If we sampled 40 households from each village and estimated the same indicator, which village estimate would we be more confident in? Think about the fraction of the population that's being sampled. We would be more confident in the estimate from the smaller village, right? Because we capture 1/2 of the total population in that sample, where we only capture 1/6 of the total population in the larger village. In other words, we gain confidence or precision in our estimates when the sample captures a larger fraction of the total population. In sampling terminology, we call this the sampling fraction. The sampling fraction f is equal to small n, the sample size, divided by big N, the population size. In sampling terminology, we refer to small populations, such as the population of a village or a health center or school, as finite populations, and we think of very large populations, such as the population of a province or a country, as approaching infinity. A sample of, say, 500 people in a finite population results in greater precision or less variance than in an infinite population. Here are the equations we learned in the simple random sampling lecture to estimate prevalence and variance of prevalence. In small populations, we can adjust the variance estimate down, making a narrower confidence interval with something called the finite population or FPC factor. The finite population correction factor is equal to 1 minus the sampling fraction, and it is simply multiplied by the variance estimate. Before I move on to an example, I should note that Stata's definition of the finite population correction factor is what I have defined here as the sampling fraction, small n over big N. If you are entering a finite population correction factor value in Stata for an analysis, be sure to give small n over big N and not 1 minus small n over big N. Stata's survey set or SVY set statement allows us to define the survey design once and then call on that survey design anytime we produce an estimate or model from the data. Let us go back to the example of a village with 80 households. We want to estimate the percent of households with a bank account in that village. We randomly sample 40 households and administer a questionnaire to one adult in each household. The questionnaire responses are captured in the dataset village.dta. In Stata, we first generate a value for the finite population correction factor, which is equal to the sampling fraction, little n over big N, or 40 sampled households divided by 80 total households. Then we define the sample design with a survey set statement. In the sample, observations are uniquely identified by the household ID, and the finite population correction factor is equal to the sampling fraction variable that we just generated. Now that we have defined the sample design in a survey set statement, we can estimate the proportion of adults with a bank account using the proportion statement with SVY:. Learn more about the SVY: commands in the Stata survey analysis video. This output shows that 55% of households in the village have a bank account, with a 95% confidence interval of 44 to 70%. What would the variance estimate be if we did not apply the population correction factor? Let us look. Without the finite population correction factor, the 95% confidence interval is wider, ranging from 39 to 70%. This is because Stata assumed that our sample of 40 households was selected from an infinitely large population. In population surveys, we almost always sample without replacement. What does this mean? Imagine the population as a big bucket, and each member of the population is a ball in that bucket with a unique number. Sampling without replacement is when we reach in, stir the balls, and select one ball at random, and then keep it outside of the bucket when we select the next ball, and so on. Sampling with replacement is when we sample the first ball, record the unique number, and then put the ball back into the bucket before selecting the next ball. The first approach, sampling without replacement, is the standard in population sampling because A, there is no need to collect the same information from the same household more than once, and B, calculation of the sampling fraction and variance is far easier without replacement. When you put a sampled ball back into the bucket, its probability of being sampled again is now unequal to balls that have not been sampled. You can imagine how complicated it is to track these probabilities with each draw. If for some reason you are sampling with replacement, which is rare in population sampling, you should not use a finite population correction because the total population, big N, stays constant with each draw. We should downward adjust our variance estimates when we sample a sizable fraction of the population. This often happens in studies of a particular clinic or health catchment area. However, if you are trying to extrapolate results beyond your study area, the finite population correction factor is not appropriate. For example, if you study patients at 3 clinics across a province to extrapolate results to all patients in that province, the finite population correction factor would not be appropriate. The finite population correction factor is only appropriate when your interpretation is limited to your study area. It is always more conservative to ignore the finite population correction factor in analysis. This means your variance estimates will be wider and your interpretations about significant results will be more conservative. I want to acknowledge that this presentation was based off of learning material developed by Dr. Bethany Het-Gauthier. Go to populationsurveyanalysis.com for a PDF version of this video and other learning materials that support your analysis of a population survey dataset.